Hello, calculus fans. Going to make a video where I talk about trig substitution. In a separate video, I'll describe this so-called triangle trick. So I will do that in this video, but in a separate video, I'll go into it in more detail. So if you get stuck on this, know there's another place you can go for even more help. The idea is fairly simple. I'm going to do it in class. I've already done some examples, but I'm going to add some more here. This is actually the most important example because this has to do with circles. This is in my mind that I tried, years ago I started to think, why do we teach this method? What's the key? And the key is this is a pretty important problem. How do you find areas under circles? Now, if you're trying to find the entire area, it's a half circle, and you can do 1/2 pi r squared. But if you're trying to break it up in any other way, then this integral becomes really important. And years ago, when I was teaching this course to an honors class, I turned it into cutting up pancakes. And I had this exercise where they had to cut up a pancake into thirds. This way, I said, you're cutting up a pancake for your 3-year-old, and you cut it up like this. I first had them prove that it's impossible to cut it into ninths. You could try that. And then I had them try to figure out exactly where to cut it in order to cut it into thirds. And it's a really kind of messy number. But what they had to do basically was to label this A, label this negative A, and say I want the integral from negative A to A of the square root of 4 minus x squared dx to be 1/3 of, I guess in this case, a half pi r squared. Pi 2 squared. And then they had to solve this using a solver. But they couldn't do it unless they could integrate this first. There are quite a few situations where circles come up. This is not the most common type of integration. It's pretty rare, but it is an important special case. So the question is, what do we do? Well, what we do is we make an identity appear. That was the whole idea. I already did some of this in class, but I'm doing more examples. And the point was that we have this identity that says 1 minus sine squared of theta is cosine squared. And if we could make that appear, then that would be kind of nice. And if we knew cosine was positive on a certain domain, we would know this. So there's a few little pieces I kind of said there, but the main idea is to make 1 minus sine squared appear. Now the problem is there's a 4 here. That's something we can overcome. The way we overcome it is instead of writing sine, we write 2 sine. The reason we write 2 is because after we square, I'm going to leave some space. 4 minus 4 sine squared. Then it becomes a 4 because we're squaring. And then you can factor out the 4, which is going to be a 2 when you do the square root. And then you're going to get this. So you're going to get the square root of 4 cosine of theta. So you get 2 cosine of theta, as long as cosine is positive, which it is in the principal domain of sine. Read your textbook for some of those details. I worry about practicalities here in our class. Okay, so anyways, what do I have here? This is going to become 2 cosine of theta, and that's the whole reason we have this technique. That gets rid of the square root. But, and this is a big important piece, a lot of students forget, you can't forget dx, and dx would be 2 cosine of theta d theta. So this is going to be 2 cosine of theta d theta. And when all is said and done, I'm getting 4 times the integral of cosine squared of theta d theta. And there's step 1. It's all about this idea. Step 2 is then to use 7-3 methods. So 7-3 methods have a very particular technique when this is even. 7-2 methods, sorry. So when it's even, we bang it over the head with the half angle identity till we're done. So go back and review 7-2. This was this half angle identity. And then you work on that for a bit till you've got it as clean as you can get it. 1 plus cosine of 2 theta d theta. And so it's going to be 2 theta plus 1/2 sine of 2 theta plus c. And let's clean it up even a little more. 2 theta plus sine of 2 theta plus c. Okay, that step is done. Now this step is the step that could be easier or harder just depending on what sort of 7-2 problem you get. Last step. We're going to use the triangle trick. Now, here's what's going on here. We have this substitution we did. And the one comment I'm going to make, maybe I'll do it right here, because we're going to need it in a second. This is the half angle identity we used. Again, this is very specific when you're dealing with even powers. We didn't have a sine squared, but I'll include that here as well. And we talked about these when we were doing section 7-2. And then there was one other identity I included, which was this one. And I mentioned that there's a certain place where you often have to use this, and we're about to use it. Very often we don't want the half on this side, we want it on the other side. So I'm just making a comment that the moment you are doing, and these are the same, hopefully you see that. You don't need to write down both. One, I put the two on the other side. Whenever these half angles come up, you often are going to need all three of these. And here's a situation where this happens. Okay, so we're trying to return to x. And what we know is that x over 2 is sine of theta. And watch my video on the triangle trick, but we should immediately be thinking of this right triangle, and we should be labeling the opposite side x and the hypotenuse 2. So x, 2. If you watch my video, I'll explain how you can quickly get this other side, 4 minus x squared. We can get any other trig function that involves theta. So if I had cosine of theta, I would know that it's adjacent over hypotenuse. But there's a problem, and the problem is that this is theta. Again, all of this is coming from my substitution, and this is 2 theta. So if you want to simplify that, you first need to turn into theta, and that's where this is important. So if you really want to know how to nicely do antiderivatives of functions involving circles, then you are going to need this identity at the end. So I really want to show that in class. So this is then 2, and this is the square root of 4 minus x squared over 2, and this is x over 2 plus c. But we still have this hanging theta here, and there's no way to make that look nice. We're going to say theta is inverse sine of x over 2. You could also say inverse cosine of this and many other things. But typically the way this is written is 2 inverse sine x over 2 plus 1/2, because these 2's cancel, you still have a half, of x times the square root. We usually write the x first because otherwise it's in danger of falling under the square root. That's how you integrate a half circle. That's how you do areas under a half circle. Okay. So let's peek at my notes here. Okay, so you can see it worked out here. There's the answer. I'm glad it matched. This is when I had my students cut a pancake into thirds. They found out that A had to be 0.529. And then I had an honor student that turned that into a bigger project years ago. Anyways. So that's kind of most, an important special problem to know. In doing that, we get several other things for free because the exact same ideas work if this is a plus or if it's x squared minus 4, but you have to use a different trig function to make the identity appear. Okay, it's going to take some practice. All right, maybe what I do before I talk about completing the square, I'm going to separate these into a few different videos. Let's take a peek at the 7-3 homework. So I hope that this homework goes pretty well for you. This one tells you the substitution. And again, there's basically 3 things you need to do. So when you plug in, you're going to get a 27 tangent cubed on top. On the bottom, you're going to get, and that's the key, the square root should go away. It's going to be 9 tangent squared theta plus 9. And hopefully you see that it's going to be, after you pull the 9 out, it's tangent squared plus 1, and that's secant. So the whole point of this method is this is going to be 3 secant. And then you can't forget the derivative. That's the most commonly forgotten piece. The derivative is going to be 3 secant squared. So that's step 1. So I'm just going to do some of the first steps of some of these problems. Then you're going to integrate, and at the end of the problem, you're going to need the triangle trick for this. And the triangle you should be drawing should have tangent of theta is x over 3. So it should be opposite, adjacent, and this should be the square root of 9 plus x squared. So this problem is just having you do those things. Similarly in this one, right, it's t squared minus 4. So we're going to try to make this identity appear. And in order to make that identity appear, you're going to have to replace x with secant. But you're going to need to put a 2 to cancel off the 4, and you're going to plug everything in. There you go. It is a little better, the problem's shorter, if you try to solve when this is for what's theta. And that actually isn't that bad. If you get your unit circle out, it's going to be pretty quick to figure that out. A comment on this one, if I was doing this problem, I would rewrite it like this. And that makes it a little easier. And then I would just try to think about what does 8x need to be in order to make this one of our identities. So these first collection of problems...
I didn't understand that.
My phone is trying to answer a question here. Anyways, I'm going to stop there, and I think I will add some examples